Hi, my name is Om Malade and this is Lab 3, Blackhole. Introduction. Purpose of this lab is, in part 1, to find the mass of a black hole using an orbiting star and its property, and in part 2, to find the initial velocity needed for a starship to perform a flyby near the black hole without crashing into it while launching from a nearby planet. This lab uses the following models and fundamental physics principles. Firstly, force in an object is gravity, which is a non-constant force. To calculate this force, the universal law of gravitation is used. Secondly, Newton's second law or the momentum principle is used to calculate the effect of force on the change in velocity of the objects. Finally, the position and velocity update formula is used to update the object's velocity and position according to the other principles used. And all of these principles can be seen in the equations here. A quick preview of the final results. The mass of black hole according to my calculations was 8.9 to the 10 to the 33rd power kilograms, while the initial velocity needed for the starship is the velocity vector seen here. Part 1. In this part, I found the mass of the black hole using an orbiting star. Since I was finding the mass of the black hole, that was my system, while the star was the surrounding. Some of my initial conditions were the mass of the star was 2 to the 38 kilograms, initial time was 0 seconds, delta t was 1 day or 86,400 seconds, while the gravitational constant was 6.67 times 10 to the negative 11th power. Here you can see my code and the resulting computational model from it. This code uses the momentum principle, specifically the change in momentum and the change in velocity, to calculate the net force on working on the star, which allows you to find the mass of the black hole using the universal law of gravitation. The code highlighted in red allowed me to calculate the mass of the black hole, which turned out to be 8.9 times 10 to the 33rd power kilograms. In part 2, I was trying to calculate the initial velocity needed for a starship to launch from a nearby planet and fly close to the black hole without crashing into it. In this scenario, the system was the ship as I was trying to find the initial velocity for it, while the surrounding was both the planet and the black hole. Here you can see some of my initial conditions. For example, the black hole mass was the one found on the previous part, while the gravitational constant was the same. The mass of the planet was 9 times 10 to the 28th power, and this mass of the ship was 7 times 10 to the 10th power, and the change in time this time was just 1. The code in this part used the universal law of gravitation to find the force working between the three objects in the system and the surrounding, which will help it calculate the velocity and the positions of your object. This allowed me to test initial velocities and see which initial velocity allowed my starship fly by the black hole without crashing into it. An initial velocity that was able to work successfully for me was negative 2 times 10 to the 7th power in the x direction and 6 times 10 to the 6th power in the y direction. The graph shown here shows the motion of the starship according to this initial velocity. So, what do the results mean? This means that the net force equals the rate of change in momentum as well as the product of mass and acceleration, as that's what both the formulas and my computational code showed. On top of that, it showed that F net perpendicular was perpendicular to the motion or the change in momentum, while the F net parallel was parallel to the motion in a chosen instance. Some possible errors for my lab were they could have been computational error, both from the code that I typed and from possible compiling of that code. There could have also been errors in the manually inferred initial velocities that I was testing. What if the spacer was to enter an orbit around the black hole instead of just flying by? Then you would need to find a certain speed which would depend on the radius of the orbit, and it would be inversely proportional to that value. One possible initial velocity that I found that worked for this is seen here in this vector.